So I'm going to talk about a torque. I wish I could do the video, the live, so you can see my hands. I'm going to talk about a torque action that took place in the canopy. That now I think I have a new mechanism that might. I'm going to do a long video, but this is going to be a short one. A new mechanism that shows the beginning of the failure. And we're going to talk about something that's going to be totally different here. And it's not totally different because I talked about what came first, the canopy or the deck. But I never talked about it in this capacity because it came to me last night as I was, well, whatever you guys call dreaming, I call it dreaming too, but it's working. I'm going to talk about a torque action that took place in the canopy that caused the failure. And we need to get a profile of the rear end of this thing. And man, I wish I had the live stream, the ability to show you the camera right now. Okay, so this is the canopy. I'm going to talk about this end of the canopy when they released post tension in number 11B and A, but 11B what held this canopy in equilibrium left and right. Gosh damn it! Bear with me, guys. Bear with me. So I hope that wasn't bad. And I'm going to talk about this too, these supports. I don't know the weight of these supports. I would love to know if they're 4,000, just Jersey barriers right here. Are they 4,000 pounds? And that's 4,000 pounds. And you can see it tied back to it. And here's another one here in this capacity. This one, I believe, and we're going to talk about it in more detail. This was in tension. I believe this might be one in compression, and this might be in tension, or vice versa, based on that torque action that the canopy is putting on the deck. From here in the base of 910. And wait till you see how I get to that. Sorry, I got to leave this open. Well, I'll never be able to close this thing down again. This is the OBS. If you guys ever live streaming, OBS is what I use, and it's the most user friendly at this point for me, because you got to learn each one of these damn things, and when you learn them, you try not to learn a ton of them. Okay, so I'm going to show you the images too. But remember the tape measure failure. In the previous videos I showed the tape measure shows it's approximately 5 inches on this side and 3 inches on this side. Let's do that. This is page 29. Let's do that. Let's get you that so you know where I'm going with this. And hopefully I'll limit this video to about 15 minutes, so you won't be here long. And we won't worry about that end of the structure yet. That would be a longer video. Come on, baby. At least the screen's moving. It's not. There we go. So let's talk about this again. The deck was built along with this. I call it a cantilever. This part here sticking off of the deck. I call it a cantilever because it's unsupported. This part of number 12. The 12 sits on top of the deck, including this cantilever. That cantilever also holds the bar number B. I call it B. There's an A and B in here. It's not distinguished where the A is the top one and B is the bottom one, but I've consistently called the top one B. B terminates out here. A terminates in the deck. B terminates in the cantilever. It's going to be very important. I believe when they detent, so right now the bridge is being moved, it looks balanced and level. When they put it on here, being everything all symmetrical, there is no torque action going on here. There's no rotational torque. So if you imagine, damn it, I wish I had the camera. I was going to show you what this ball, the connection. If I apply more torque, if I have long bolts in here and here, there's not rather thread all. And I would have torqued this one 4 threads longer than this one to the left. You can pick anything you like on this in your mind. But let's use the canopy. If I were to torque, had a long thread all here, and I was to torque this one 4 threads longer than the one to the left, that would create more torque on the right side, correct? That would be more torque on the right side, being that the bars are equally of strength, so resistance. So they would resist different equally. So the bars are perfectly balanced, okay? They're both the same bars. They came from the same long material that they cut in half, and then they put them side by side. It wasn't even a different lot. So let's just say they ran off a 100-foot roll, a 100-foot bar, and they cut the 100-foot bar in half. It was all continuous piece. They cut it in half and said you use thread all on each side. So your bar is from the same materials. There are no ifs, ands, or buts. The temperature, the day it was made, everything is 100% the same. Let's go with that. But these are tendons up here. And the same thing with tendons. They are from a reel. So they say that the reel, the same thing. So there's no difference with these cabling. But let's say you torque this, you have this, using a thread all example will help you out. You thread this in 4 threads too much. Or let's call it 10 to help you visualize it better. 10 threads on this one, and this says 10 threads less. That creates a torque action on the right side of this structure, on the bridge here. More torque on the right, and then down here. Now, the detensioning up here, we kept looking for failure up here on detensioning in the blister. But it's too far inbound and it's balanced here. The torque action would be least able to happen here because they also have four bars inside number 10 that would help stabilize this blister. But there are no extra stabilization happening down here. And I always tell detensioning would release, so you have this torque action going on up here, and yeah, this is live, right? So you got to bear with me when I stumble. So remember, when I go backwards, when I say stumble, I'm going to go backwards, digress. Remember when they post tension in the structure to begin with, when it was still inside, and I know visually you guys, I visualize it, and I need to help you visualize it. When it was still in the staging area under with the scaffolding on it, let's back this up. Come on, baby. With the scaffolding on, I'm going to the scaffolding image just so you guys know where I'm going with it. With the scaffolding, come on, and then I'll go back to that image again. So scaffolding's up here. I apologize for the screen flicker. Okay. Too far. But we'll use part of this. Rotate clockwise. So we used part of this. There were scaffolding in here, scaffolding at the base, and scaffolding here, support scaffolding. False works here and here, scaffolding, same difference. This scaffolding was their false works, incidentally. So the scaffolding is something you normally climb on, things like that. False works are supporting. That's for clarity on what I'm telling you. It looks like just scaffolding, but it's false work when it's holding up a structure. This is wheeled. It appears to be wheeled. So this is scaffolding that they're using to possibly gain entry onto the top of the canopy, the scaffolding here. And they're not using a man lift or any other means to get up top, apparently. So maybe they enter here, there's the fall protection, then they climb the scaffolding. Well, that doesn't make sense, does it? Because this scaffolding doesn't appear to go to the roof line and above, which would be a safety issue. But what goes there is this ladder, so this is what they climb up on. So the scaffolding here is used for the underside, or, well, maybe they were doing something here. See no other materials lying here, like a pump or anything else. But the scaffolding's here doing something. They're doing, and it's on wheels. So they're doing the full length of whatever they're doing here with the scaffolding is interesting is noteworthy. Because they have the scaffolding there while this is here, but I think this was here a couple days before, a week before they hired it or something like that, of that nature. Well, so the false work scaffolding, I keep using it interchangeably. So this, imagine if they're before, and we're going to talk about that torque and compression over here, and same thing there. Let's go to the scaffolding / false works. So right now, this is noteworthy that the bridge is being moved. As it's being moved, if it had a torque up here right now, or in the base somehow, that twisted this structure. Let's call it that, twisting this like a long twist. It's an I-beam. You can twist an I-beam. So let's imagine you torque this. This I-beam is only symmetrical upon these loaded members here, these diagonals and uprights. And you know, I like to call this an upright. I would not like to call that an upright because it's only a little bit out of plumb. So if I can't call this an upright, then I can't call these uprights because these are out of plumb. These are built out of plumb by 2.5 inches, and this one's out of plumb also by so many inches. So if it's you're allowed so much out of plumb, but these are actually built out of plumb. So do we actually call these verticals at that point? Just a question, if anybody wants to theoretically play with that. If you look at wall systems, you are allowed in building codes, you are allowed to build walls out of plumb. There's some degree that walls are allowed to be out of plumb and you're okay. How much can a upright be out of plumb and no longer be called an upright and be called a diagonal? That's a very interesting thing there. At what point do you call it a diagonal? It's just interesting. And this is built that way. But if it was twisted like if you imagine this was long and you could put one hand here and one hand here and you were to twist it, it would reveal itself, you would think, on the shims that were required here and here compared to here and here or vice versa, that it would say you would need another 1-inch shim here. And you're like, why do we need another 1-inch shim here? Shouldn't this be perfectly level? But do these riggers, do these supports allow for individual elevation? So in other words, this would be more data during transportation. Did these things go up and down? Of course it would on the road here, but over in the staging area back here, would the ground have been perfectly level before transporting, or is this up and down? I don't know. That's just a rabbit hole. So let's go to the staging area and look at the false works. This is our failed section, and here's the ladders beginning on top of the scaffolding, and then there's your ladder again to get on top of there. So I don't know how many feet that is, and then this appears to be scaffolding leaning against there of a very tall nature. That's interesting. Interesting scaffolding leaning against there. But this just looks like typical scaffolding. This doesn't look like, really false work scaffolding. But and that was also what I found interesting, that they didn't support the base. And Fig has a history of knocking down, making base scaffolding or false works small or insignificant. Fig has a history with that, with the bridge that collapsed and killed those workers, and I forget which location. And then they redid the damn bridge. It's the one with the anyway. Yeah. So that would be consistent with the engineer of record. Engineers of record, Fig Engineering. So we have, because I don't know if Denny Pate was the engineer of record then. I don't recall. I did a slight video on that. But we see this scaffolding is just sitting on pads. This is not anything poured here. Nothing protecting the pads around. It's just, and this is for the possibly the working station out there. But these look like just pads here also. So point loading definitely could be taking place on this false works. I talked about that in another video, but this is where I'm saying that imagine that long twist, that torque action, because they post tension D1s and then C1s. No C2s for clarity, because I've said that numerous times. I think it was then C2. C is being canopy tendons. For clarity, I looked over that again. It's C1 only up here, and then they commence to tension the rest of the deck. There's no statement that says that they grouted after they tensioned. After they tensioned D1 and C1, in the engineer drawings, they do not say after tensioning C1 and D1s and C1s grout. So they did this ungrouted. To me, that allows for some flexural movement without identifying itself so easily within the ductwork of this long span. Yes, it's supported, but it still allows for, it's inconsistent. It doesn't. There was no slippage though. A lot of people would just say, well, you would see slippage if it started doing that at the anchorage, if it started deflecting. Well, I would say you would see elongation and maybe no slippage in that long tendon, this long theoretical tendon with these loads on it. All right, but you would see, but not but. Also, the engineer that did the inspection said that they said after tensioning, I think it was number 2 and 11, cracks appeared in number 10. So after tensioning this, then they did tension D1s and C1s. That's on each side of this structure of the center line. So C1, C1, D1, and D1 along the next two on opposite sides of these verticals. Okay, we'll just call them verticals at this point and upright. For people who might be triggered by me calling a possible upright, so I'll hit both of them for you. Don't want to trigger you, I just want to share the information. And you know, psychology, I love it. If you're triggered by one thing, it can stop the message. And so I'll address that now. Noteworthy is this long board going across the top of here. It does look to be flat. It looks like 2x4 with a skip here, holiday here, and then continuing down the top here, and it looks like it flies over the outside of the structure, which would be the top. Apparently, at this point, I might be getting visually messed up. No, this is the man protection, anti-fall wear, if you will, of the scaffolding that goes on the out right here, goes up. It's for the face for them to get to the face of this. So, yeah, I saw that wrongly. I can see it now anchored here, but it's a good line to work off of still. So I thought it was sitting on the blister. It is not. So as we look at this, and just visually, and the camera could throw us, but that damn thing looks pretty flat. And a 2x4, come on. But nevertheless, damn, that looks good. So I take the good with the bad. All right, so we talk about those supports that were temporarily holding it to the sides when they had the machine here, when they had the transportation here. Look, 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 look. As the joke says, looky, looky. Anyway, it's not here. They're not here at this point. Those temporary bracing are not presented in this image. We don't see those temporary bracing holding the diaphragm of number 11 and 10. And let's look at that real quickly. Let's scroll up so you can get the data. And come on, baby. I'm going to let the screen stay like this. I'm going to have to rotate it. If I have to rotate it, I'll rotate it at that picture. Oh, let me zoom in. I think I can do this a little more, 2 pages at a time. Here we go. I'm just zooming in, and then we'll zoom back out. Yeah, that's going to be much more user-friendly. So we just saw that there are no supports there at that point. But aha, now all of a sudden, bracing of the north end of the span, the truss formwork and shores had been removed. Well, when was this added? When was this added and why? And why? It wasn't added before when they had the false works there. So I'm going to talk about that torque again. That apparently, unless they're worried about some uplift and hurricanes flipping this damn thing off the structure, which doesn't make sense because when they put it on there the day of the move, they didn't anchor down the supports. So if they didn't anchor down the supports at each end, well, how is it that they're worried about hurricane and twisting, blowing off and safety at this point of the game, but not when it's over the roadway? So I find this to be very interesting, of a very noteworthy nature, differently than the OSHA report. That this was thrown in there for what reason? And yet these are built-in, designed in there. These don't look like last-minute epoxied-in anchors when we see it in the structure. And they're not there during the scaffolding installation. So therefore, I can use logic and say, well, these are after you remove the false works and the scaffolding, false works, that the engineers decided that, or at some point, that this will be needed for what? For hurricane again relief? For this thing being wind and twisting it off of this lift? Why? But inadvertently, I think this acted in, and without knowing, tension and compression. If you guys remember, I did that Christiana River Bridge. I went down there in the heat of a major hot day, and I grabbed hold of the supports. It's a post tension bar loaded bridge. It has an arch on it like this, and it's held by hangers by the bars, and they're spaced approximately 4 feet apart. And you might have seen me go down there and grab some of the bars, and a couple of bars I could grab, and they were like totally loose. And I was like, check that out, guys. There's no load on this at this point. The heat of the structure, just between an 8-foot span, has released the load on this one bar. So theoretically, you would think it would all be under load, but no, it was not. It was this bar I could grab and shake. Well, the same thing with this. If you could only use some logic, common sense, you'd be able to figure out which one is in compression and which one's in tension, literally by grabbing hold of them and seeing which one if they flex. Well, then it's loose. If it's tight as a drum, it's either in compression or tension. Compression might show a buckling one, but they probably aren't both equally compression and tensioned. Here and also here. And I say that because, you know, how that it's some torque going on here that they theorize is going on here. Because here it's laying, as the engineer report states, it was fully supported on the entire length of here. This is per Denny Pate's presentation, that it was equally, so Denny Pate's F dot. So I got to go to F dot then to show you that, because I realize F dot fig analysis presentation. So it is fully supported, and maybe I can do this. Maybe I can find it. So Command F, fully. Come on, really? Okay, 1 of 3. Bridge was loaded on the permanent supports on 310. Oh, this is FIUs, not F dot. On 313, email FIG documented regarding the cracks, and FIG instructed MCMs to install the recommended on 313 shims in the pylon base directly below member 12. So on 310, it was moved. The collapse was on 315. On 313, MCM emailed FIG documentation regarding the cracks, and FIG instructed MCM to install the recommended temporary shims in the pylon base directly below member 12, node area between the permanent support shims. So FIG told them before the failure, put the damn shims in. And time of the failure, we don't know if those shims were really installed or not, but apparently they were not. And the question is, are the shims the recommended temporary shims? The temporary shims, is this the grouting? It's permanent grouting, right? So this is ambiguous on the shim thing. Shims grout. They both are mentioned, and so not here, but they both are mentioned. But the problem here is it says the word temporary shims. The shims are never going to be removed. You're not going to grout and then find a way to pull out the temporary shims. So I don't get these temporary shims. The first stage A shimming, and then grout around the shims, and then the first grade A shimming stays. So this temporary is a wrong word. Temporary implies that it's temporary, that it will not be permanent. So this implies removal at one point. That's not logical. But here's also, FIG assured there was no concern for safety of the span suspended over the road, which is ridiculous because we know that they did not know the cause of the cracks. So we look up cause. Concrete is sticky flow, but because of the titanium dioxide FAU concern to be used under the pylon diaphragm. Right, this is going to be pylon. Second word of cause. Okay. Let's see. Did not. Okay. Not. How about now? FIG responded that all we know is that it just happened. This is FIG's reference of cracks about F dot to FIG. Are you going to continue to figure out why it happened? FIG, responded, all we know is that it just happened. That's all they know. It's when you say all, that's like saying all on everything. Look, I don't care. I want it all done. There is no exception to all. So all he knows is that it just happened. That's it. That's the all. That's the total encompassing knowledge of him and these cracks, based on FIU statement of it, also based on FDOT statement of the same report about the cracks. We'll just use the FIU version of it. So he has no idea how the cracks happen. They just happen. This is per FIU reporting what FIG stated in quotes, and FDOT does just about the same. So they have no idea how this happened. Now, I'm going to give you back to this again. That the C1, I think, created a torque that the canopy was not balanced, and I'll get to it right about now, and then I'll give it the backstory again. So let me zoom back out. Okay, and then we'll come back down to the failure. This is the torque action I want to show with you again. So this is after post-tensioning. It cracked like hell. All right, it cracked like hell. This is the post-tensioning guy that reported this, and these are his images from his cell phone. 9% battery. Wow. Anyway, so those are the images from his cell phone. It cracked like hell. This is the critical part that shows that torque action. The cracks are too. So this is the engineer that took this image, and you guys already know how I feel about this engineer going from D2, I believe this is D2 and this is D1, and going from the side of D1 on an angle down to roughly mid between D1 and D2 on an angle. You do this damn thing plumb, and you go to the same spot. So here's 3 inches here. Let me zoom out. It's going to make it faster to go to the next one. And then this is the other side. This is the other side, rotate counterclockwise. And this is underneath for D1. They're about center line of D1. And now we see that we're at approximately 4 to 5 inches. So there's a 1.5 to 2 inch rotation, being that this is parallel. The base is parallel, and you see the gap, and that's my cantilever I talked to you about. It's unsupported. This number 12 is an unsupported area. There are no shims under there. So we'll put the load directly back down to the pier. No shims. So therefore, it's a cantilever. So when they detension the back of, I'm zooming out a little bit, when they detension B up here, it no longer had the clamp force to help hold this cantilever into the deck. The tension, correction, the clamp force that held part of this if they had shims under here, the forces when they detensioned number B, I'm calling it B back here, is in cantilever. It's inside the cantilever. Bear with me. It's inside the cantilever. So when they detension, I'm gonna tell you where I'm going with this. It's again, torque in the canopy. Torque in the canopy caused this failure. That everything in my brain says that all my logic says that multiple engineers looked at this. They all said it should work. That I'd have to state that all of the design software, that the engineers' calculations, that FDOT, that FIU, that Denny Pate, that everybody who looked at this didn't figure out that this is being, not facetious, but this is being me going at myself, know how to attack myself. I would have to state that they all missed that all the loads that they put in the deck would not hold the bridge's weight for deflection. And that logically would say, wow, that's a lot of people that kept seeing the same mistake, which is totally capable of happening, as we see in the meeting at FDOT. Not one person said, you know what, this logically doesn't make sense. You just stated you don't know how these cracks happen, and yet you're saying it's safe. So if you don't know how can you say that? So I can prove to you that we have groupthink here and following right here, this right here. Every engineer that was there, all of them went behind Denny Pate. But I told you that they wanted that, hey, let Denny Pate jump on it. I told you that. You're like, in your hindsight, maybe they are good engineers, a couple of them, but they're like, you know what? I'm not going to speak up because Denny Pate's the one who's going to lose his license, and maybe some of them don't like Denny Pate. They're like, F it. I don't care if it fails. Psychologically, you see how in the other groups they're haters amongst engineers. And how do you get rid of an engineer? Well, let him kill people, get rid of himself. Sort of, it's a lot of hate there. And also, there's a bilingual thing, and you're dealing with somebody who claims to be superior in their knowledge than the rest of you. So you're scared to question the superior person. All right. So the coupling. See the couplings here? They were inside that. That mechanical coupling. There's one on each side of the structure. It will be this one and I believe this one then. And that's what we see at the top of the structure. And these are the pins. Well, that's just right. Mechanical coupling. That would help hold the bridge down with the same intent, I would think, as those braces we looked at, the side braces. But I'm going to show you now, I'm giving you the backstory data. So I was coming over here for something. Let me scroll down. Hold on. There we go. And come on. I'm getting to it. The screen is on. This is a live website I'm on. So it's got some, talking issues with my computer, I guess, and live. Yes, it's right there on the screen, right here, as soon as I get the thing to move. Okay. Oops, too much. Okay, I might want to grab the one below it. I like it. It's scaled. See this page? I'll tell you why. See how much it takes up a full page? This takes up half a page. So I'll be able to get more details out of this one for you. I'm waiting for it. I moved it, so I'm waiting for it to recognize I moved it. I guess I didn't move anything. So this is that B I talk about that's outside. This is B. It's outside in the cantilever, I call it now. Cantilever being this part right here. Since it's unsupported and it's load-bearing, it's a cantilever. And I'm stating it's load-bearing. And because it's a structural load-bearing. And this clamp force is, instead of it clamping from here and pulling this direction, when the clamp force more than likely is probably from this direction, holding this on now. And yeah, I know I said before that the clamp force, we talked about clamp force, but now I'm giving it a different direction of this clamp force. From this side, holding this on, holding the back of 12 on. It's unsupported at this point. So when they release this side here, the cantilever and the loads coming down, remember this triangle, coming down 12, were released. That it was actually because the canopy was structurally holding this bridge together also from deflecting. And that was in C1 and C2. C3 and C4 were not done yet, if I got that right. So it was also it was acting as a strong back, but it was tied in at the base. So this triangle worked only when the B was holding it together, was holding this triangle together. When they released B, the triangle was no longer held together at the base here. The deck had a moment of a drop down. A drop down, which of course would hunch down number 12. Number 12, hunched down, did the crack like hell. But then this rebit and held the deck from falling all the way to complete failure, I believe. I believe this rebit because this was only loosened, not removed. They didn't say remove the nut. If you remove this nut totally, I would theorize that this whole thing would have went down right then, that there would have been no rebite. So we're looking at a rebite here at this point of number 12, a jerking motion, and also the torque. So when they release this, the canopy is, if all things being symmetrical, that this should not reveal itself as such. All things being symmetrical, they slowly releasing it. You know, you're releasing it, it cracked like hell. You're releasing it. Here we have approximately 5 inches over here, and let's call it 3 on the other side for round numbers. 1.5 inches sounds kind of weird to do it. So this is showing that the bridge took a rotation. The canopy took a rotation. The canopy, not the deck, because we have symmetry here. This we have a lifting, a high on the back end here, and low on the other side. But the diaphragm appears to be equal in height from here, where it's not cracked, to the top of the pier. And same thing from here. So from here to the top of the pier being level, let's call it, and from we're past the crack point being level, that shows that this cracking has already taken place, and a rotation is taking place in the canopy at this end. So if the canopy was so symmetrical, then there should be just an equal hunch down, no rotation, just like this should be no rotation. Theoretically, no rotation. You just released it slowly through detensioning number B. A doesn't really count for me. Upon detensioning B, it does that. Now this signifies that the canopy is hunching down, but along with the deck, because number 10 and the rest of the deck have no statements about it buckling or anything else. So if they're not buckling, well, then the buckling is taking place at that triangle. If these aren't buckling, the buckling is taking place right here. So from here to here, we already have a slight moment going on here and here, where the cracks are going to, where the bridge ultimately fails. That this is very stable and very stable. And this is where we're getting our deflection here and here, with the triangle here losing its base structure here, causing it to go up, rebite in number B. That gives us our look. The rotation is already taking place now. If we look at the rear end of this thing, let's find the rear end shot. Let's discount that for a second. Not discount it. We don't need to see it. We already talked about it. So this rotate clockwise. So this is our rotation, showing that rotation. Doing the rotation, this is what happened to number 11. This part of this triangle torqued. So this torqued separately. The canopy torqued separately. The canopy and the upright torqued separately, twisting the base of here out to here, showing it's revealing itself back to here before the rebite of number A and B, more so B, stabilizing this again to the point we're looking at it. Remember, they don't know what the cracks came from, and that's my whole thing. The cracks tell the story. So they're stabilizing. You know what? I didn't check the audio on this whole entire video. Let me check the audio. This signifies, right. Hey, Seven watching. Hey, Luna. What's that say, Luna? Yep. Okay, thank you. No special glitz. Yep, Luna, I'm with you, baby. All right, let's get to it. So getting back to this. So the rotation happened. Let me move that there. I got to be able to get it. So the rotation took place, as we see here, identifying it. This is the rotation. But the bridge didn't rotate. The deck didn't rotate to make this rotation. So if the deck didn't rotate, we know the deck didn't rotate. It's sitting on top of the damn shims. Nobody's reported that it's lifted off the shims at all. the existing shims. All right, so no one's reporting that in this report that, oh yeah, the base of the structure is twisting. It's off the canopy. I mean, it's off the pier cap, off the pier. So so if you have a separation like this, you're having that torque, and that's identifying itself. This torque took place as the dropping took down. The torque is at the lower end of this triangle. So we can see here the lower end because we see it's connected here. There's no cracks identified here. So that's why I'm stating the lower end of this triangle did more of the torquing, and we see it in the tape measuring. But right under here, if we look at this joint, no one's revealed any cracks there. We can find, let me zoom out and get you we can find, so there's that torque, that rotation I talk about. We can find the crack going up here to identify more of that torque. And yes, see how large that torque has identified itself over here? But over here it just shows itself as just a slight bit of torque, right? A slight bit of torque here. Amazingly, I talk about it dropping down. Remember, I got to fight myself. If it drops down, how is it so if it's dropping that I don't see compression here then and crushing at this point? Because this is more of a hinge action of a torque. So it drops down in hinges, torques, and this makes room for it to drop down. So this part is overlapping behind each other. As you can see, a little bit of overlap right here. But at the end, in the back end, it's reflected itself at this distance. So a quarter, let me explain to you. If I only move a 1/4 inch per foot, you're like, well, that's only a 1/4 inch. You never see it. Yeah, if I go out 10 feet at a 1/4 inch per foot, what do you have? Right? You got 2.5 inches. And all I did was move a 1/4 inch per foot. So if I move 1/8 of an inch here, and I don't know this here, and go back there, you get that elevation. So maybe only 1/8 of an inch of movement, but it signifies itself, and conversely in the opposite. So if I move 2.5 inches here, if I go to the far end of that 10 foot, it only looks like a 1/4 inch. But if I'm at that end, it looks like 2.5 inches to me. At the one end, it only looks like a 1/4 inch out. On this end, it looks like 2.5 inches out. You see where I'm going at with that? So this is why it may look like nothing here. But in reality, to get this little crumb here, you go out 10 feet, and you might got 1 inch of movement. So these count. Cracks do count. All right? So let's get to this. And their openings count. So we have this the failure back here, the rebite, and this torque action, this rotation took place. And that's my whole thing, is that if this was all about centerline, meaning everything was done about centerline, symmetrical, balanced, it shows that it was not balanced. That triangle back here torqued, rotated. This triangle, if we look at the back end of this structure, and we'll look at it in a different view. And once it did that, watch how I put the forces down, that rotational force, that torque, down 10. That rotational torque of the canopy goes down 10. That throws off, all bets are off now on that beautiful design. I'm calling it a beautiful design because really, I don't care what all these other engineers are saying. I think Denny Pate did a beautiful design on all of his, because it just looks structurally like it would fail. And yet, and I've always stood by, wait a minute, his nodal areas are not failing. They're just beautiful. They're not failing if you look at his nodal areas. You can pick on them all you want. You can say they're inadequate. They're adequate. But what's not adequate is the whole, the bridge was already deflecting. In the impound, in the staging area, because it showed the cracking at the base of number 11 and the deck. That cracking was, as I stated a minute ago, you got a 1/4 inch here, you go out 10 feet, you got 2.5 inches. It's not for free. You don't get an opening and cracks, and it doesn't mean anything. It means something. And right about, let's zoom in. Okay. I don't need to go down that track yet, or probably at all. I know what image I'm looking for. So there again, this is A. This is in the deck. In the deck, literally, you see it in place. You don't see any failure. You don't see it blasting out. You see that it's encapsulated in concrete. You can see that the space behind this giant nut, and I forget what they call it, with the castle, with the not a castle, with the base already part of it. You can see it's really tight against that plate. So that rebite I spoke of did not create a force outward. So you would see a separation here. It wouldn't put itself back together. It possibly could when they retension, but we don't see that because it's very tight there. Well, I would like to see more images of that, but it's very tight there. It's A, the top one. Correction, that would be B in my way I evaluate it. And these are those supports, the anchors that they now covered over with duct tape, and hiding from us as the public. It seems they just keep messing with the damn chain of custody of evidence. You know, it's just craziness. These cracks, I don't think, were present right here that we saw with all the imagery. You know, they're not identified as new cracks or cracks during movement. I told you that when they transported it, that was the stupidest thing ever. That Denny Payton could have won that in court. They need that evidence. And look, they transported during the vibration of the road. Those cracks developed. They weren't there before. You know, they transported 30 miles, 20 miles. I don't care how many miles it is. They shouldn't have transported at all. They broke chain of custody of the evidence. You don't transport. You don't come to a crime scene and go, yeah, take all this stuff back to the warehouse. Just pack it up, take it to the warehouse. Let's look at it over there. Well, who's going to win a case like that? You've got to be able to have it all at there, and you guys, even though you watch your shows, I'm sure that where they show the crime scene taped off, and sometimes it may be weeks before they allow any access. Here's the back of, without having it protected. Here's the back of number 12 again. This is the one, detention. They said they'd affected the rotation right there, causes the cracks down here. Let's go to, I'm going to show you this rotation at the back end. And I find that just weird. That's the end of the structure we should be looking at, yet he's showing the non-end failed, the initiating non-end failure. And same thing like that. That's dramatic effect because it was not like that. After collapse, looking east. This is not true. This is nefarious in its wording. South end of the bridge after collapse. This is nefarious in its wording, meaning it is not true. You can technically say, well, it is after the collapse. No, the words are after collapse. This is not after collapse. This is after and during demolition. You can see the demolition the thing there. We saw it, and it's also hammering at it now. We got the work crews out here. This is during demolition. So I know the guy, I don't know if he's doing me a solid or not, putting me in the report and all that, but this is not me. I can't stand, I can't stand defects, okay, so there's about the same rotation, this time without the crane in the view, apparently without the crane in the view. I say apparently because maybe a larger image shows it, and this is a cropped image. All right. This is the rotation that took place right here. Is that this torque took place down after the detention. Torque took place in this canopy, rotating and putting a torque action on. So yeah, let's just do that real quick. You see that tape? Let me zoom out. Let me do a confirmation. That was the bottom. I thought it was at the bottom. I'm looking for the end. There we go. So right here. Duct tape is here. Duct tape is here. No, you see no diagonal cracks at this point presenting themselves. Yet during movement and during cutting of the structure, they created cracks and required duct tape to, for whatever reason. So here's your duct tape now, and now here are cracks. So how is this even, how is that even evidence of anything? Yeah, I find that just stupid. That's just stupid. Now that would, like me trying to evaluate this. I'm going to give you a whole lot. I need to evaluate how these cracks developed and everything else. And I'm going to give a lot of credit to these cracks now. And yet they didn't exist at the failure. So it's just nasty. Let me get you the. So this NTSB report we're having coming out is just craziness. Talking about that torque effect down there. Where are you, baby? So this is before the collapse. Let's right clockwise, right. This is before the collapse, right? So right now we're looking at that this has been retentions reportedly. And it's reportedly twice. One in the OSHA report where they said they completed close tensioning, and then another part of the report he states that they were working on the last one, detensioning, the last round of detensioning. So, it's multiple statements in there on that in the OSHA report. So after this drop down, we know the tape measure is higher over here, meaning this is higher here and lower here. How do you get that? You can't get that, and remember I explained to you about 10 foot. And now these aren't close by. This is a 33 foot deck, but we already have our distance. This is now listed as 3 inches. But keep in mind that I'm stating 3 inches and 5 inches here, that there's a gap above that tape measure that would show that this is even theoretically has more torque on it, lower, because there's a gap, a reveal in these cracks here. So even though it's showing 3 inches, it extrapolates to more. So let's get you that, to more of a torque in that canopy. There's more torque in that canopy using that tape measure to disclose it than what's going on. And that torque is rotating, that rotational torque is revealing itself down 10. 10 is now putting a torque in the diaphragm, in the longitudinal post-tension cables along with the transverse cables. A rotational torque is in the base now and is torquing it. And so it's no longer making it out to the diaphragm as designed. That was where the progressive failure happens across the diaphragm now. I think it's as simple as that. Across the diaphragm, across the this is live, sorry. Across the deck. And, oh great, I keep running to the bottom of this and not. I'm just on a live video. Give me a few minutes. So let me get to that tape measure again. Sorry. Tape measure. Tape measure. So I'm finally happy with it. Explains the tape measure, the height. It puts it back into play about the what relation that has, that torque. That rotation is not for free. That rotation is still tied up here in this canopy. For this to rotate down here, it had to rotate up there. And remember the distance. We've got, 3 inches of rotation here. What does that equal here, up here? There's a lot of torque going on here coming down to from this triangle to this point. Because it's trying to torque the whole damn deck. But it's resolved at this point. So what came first, the deck failure or the canopy failure? Remember I kept saying that, chicken or the egg? You know, what came first? Well, I'm saying that the canopy failure was happening first. It was an internal torque going on there that also reflected itself down here, that this bridge, that perhaps the design of this bridge could take all the loads and all this dead weight of this. Sure, it could take it perhaps with all the post-tensioning functioning. And that's the confidence I said in the video what Denny Pay could possibly say, and supported Denny Pay could say, I'm not worried about it. That he could say, because think about it, guys, if you made this so this you didn't care that the dead weight, that the longitudinal post-tension cables were here to keep this from deflecting, but the steel was redundant also. That you're like, I don't care. Some cracks will develop, but you know what? The loads will still transfer here. That I know I can take these point loads in my design that it would make it out to the diaphragm. That I don't care that this is broken here, because this is designed to take it all. I don't care if you just break this all apart and lay it on my deck. This will not deflect, because all of these, this can take it all laying there. It's just as scrap. In fact, I further extrapolate, working for Danny Pate here, if you will, is that because further that is that, remember, this was going to get steel pipes on here weighing thousands, tens of thousands of pounds on top of this canopy steel, point loading all this. So this would be insignificant, this dead load on top of here, even if it was detensioning. If you detension totally, I believe, if you detension total C1 and C2. But it becomes not insignificant, if you will, if I now point load this with a torque action down here, changing it, the profile, changing the reaction in here, the moments inside these D1s, which are so small. D1s are smaller than D2 and D2, D3, D4, D5, D6. And that torque action would create, say it's a rotation to the right, this clockwise direction, right? I could say negative, positive, whatever. But let's just use a common talk here. This rotation clockwise to the right here. That would create a torque action down 10, a rotation down 10, right? A torque action that would put more force down this side of 10, and tension on this side of 10, which would have an effect of a pulling effect in D1, of putting D1 under a camber, and D1A, D1 on this side, right? And let's call this D1A, and this is B on this side. So D1A would be under a camber, and D1B would be under a rotation, a pushing downwards, right? A force pushing downwards. That would just change the profile of this altogether. So you would have a torque, but it would be out here as this torque action taking place. And you guys know what happens when you use along a bar to try to break a wrench. The longer the bar, the easier it is to break that nut open, right? So this is a long bar, that distance and this torque action. So that's not for free. This torque down here, this rotation down here is not for free down 10, I believe, because we have two brakes. We have brakes here and here, and that helps me. That helps me also with why the brake identified itself here. So I could probably argue that the torque, the rotational torque, was right here, trying to have that torque action as they try to put it back here. That it just didn't crumble. It prettily failed. So let's get to what I was talking about. Tape measure. We're looking. Forget that. That's that rotational torque happening. Rotational torque happening, and that's rotational torque happening there, identifying itself. And then we have the base. The base, I'm going to get you to that. That's, I'm going to find that tape measure again. That shows the rotational torque happening. High here, low on the other side. And let's get to that tape measure to show you the additive effect that they're leaving out. So I get to rotate counterclockwise. So I get to show that this is approximately 5 inches. I got to add in this gap here too, though, that's dropping also. Let's see, did I add that in? Let me work my brain. So that's rotating and away. Yeah, I get to add some for that. And then I got to rotate this in the other direction, I believe. Yeah. So same thing with here. I get that it's rotating down. Do I add the gap here? So the gap, you see, it drops down. Yeah, my brain's working on that gap. Do I add that 1/4 inch there? You know, the gap spacing. And what do I add from? So I would add from out here. Basically, you would, damn tape measure here, and we could see this. We can then do the additive effect of how much the structure is rotating. Too bad he didn't take the tape measure from here all the way to the canopy, to the top of the canopy on each side, like a survey of trying to figure out what's going on. Remember, that's always the problem. NTSB is going to do a report of what they could do. Well, they should require a survey of the entire structure before going forward, shoring it up, and for safety reasons. And they could have just simply measured from here to here, and from here to here, and you would have seen this rotational torque I'm talking about. In this case, it would have been from the pier cap, the top of this pier to here, and from there to there. And it would be the outside. But you'd have to take those measurements as it was placed so you can verify the how much rotation is taking place, or how much you're looking for movement, so you can figure out what the hell is going on. All right, so that's about the end of the video, basically. Let me get you back to this. Let's put this, zoom that in, rotate counterclockwise, and get you a better and so imagine the torque. Oh yeah, I could actually do that for you a little bit. I don't know if my software is going to let me play along with this just now. Oh, I've got a lot of data to share, guys, with the bridge. The Aragani Bridge. But I'm just working on this with you right now. So this does not allow me to rotate. That's just going to rotate the image. But there's the torque. Imagine it was rotating. So this rotation here down to here, if you could rotate it with your hand, put your hand on this section here and give it a clockwise turn. As you do that, you would create a torquing action here, clockwise. And so that torquing action would have an effect, I said, of putting this in tension on this side on compression, and that would change the profile of this way down to here. This would create a new moment inside this cross member here. Cross members. I love calling a lot of things members. And this cross transverse cabling and longitudinal cables in D1s, D2s, all the way across. So that would look like, let me zoom out. And I went over this in another video about the, come on. I'm getting to the, I'm going to grab the post tension, the top view of it. Bird's eye view, however you guys are, however old you guys are. All right, this doesn't move that fast. Yeah, this is FDOT's website. Oh, perfect. So I'm going to use this part of it. I think this is probably the failed end, but I'm going to use this end. Yeah, direction of stationing. But I'm using this end because it makes it easier for our brains to follow, right? So the rotational torque will be down here, and it's not down this end. Don't beat me up. So if this is the 1012. As you torqued it, looking at a bird's eye top view, right? And as you torque that, it would create these are the transverse cables, and these are the longitudinal cables. It would create a profile change inside this area here, which would no longer allow it to transfer the loads down and the transfers longitudinal cables, both actually. So that would create that torque action, and the rotation and the failure on this side of the structure makes more sense to me now. That the failure didn't happen. Remember I talked about in another video, well, I have to say the forces go all directions. This being the weaker side and is working its way out to here, to the diaphragm, it's weaker in many ways. It's weaker because there's less post-tensioning forces on this end, literally per the drawings, than on the other end. The diaphragm is already weak now. It doesn't have participate. It's so many things. Look at my videos on that. If you want the long video, well then, ask me about it. I'll link you to it. So that's the size of that. So I am pretty much done now with that. They tried to put post-tensioning back. All they did was create that forces in there, created a brittle failure. It was just sitting there, abrupt brittle failure, same difference. And it no longer had the triangle to maintain the structure. But by then, the torque, thinking about the dead load thing. So I fight myself. So if that created a brittle failure, right? And I just stated earlier that this whole bridge could lay on here as scrap. Well, then if this failed, let's fight against myself now. If this failed, well, this should just lay on there as scrap then. It should go, brittle failure should be here. It should not, therefore, the diaphragm should be okay. So no harm, no foul. That this should just, bloom, collapse on top of the deck. And no harm, no foul. But I'm saying there is harm, foul. That this torque action, because of that rotation, that this is so embedded, that number 10 in this, just like that long wrench, it already created a defect in the design of the transferring the loads out to here. That it had to have done that because this bridge probably could take all the dead loads of this just lying on here as trash. So what that this failed, it should just lay on here as trash. And they've detensioned number 12. But I'm saying that this acted as a strong back also in their design, that this was part of a strong back. That if we could only see the computer modeling and how they did it. If that computer modeling worked, that they had this in the computer model, that they did stages of the modeling, saying at this stage we're going to put it in place, and we model it that this is structurally strong, then I could argue whether the computer model doesn't work because it didn't account for, the computer model did not account for this all being cracked up, that this being destroyed. Oh wait, I'm being facetious, aren't I? Because we do have computer modeling as reported by the engineer, showing that he used computer modeling, and yet he showed no cracks in his computer modeling. They showed the structure should work great under computer modeling. They showed the shims, the temporary shims, permanent shims, but temporary, hell. Anyway, the computer modeling shows that, come on, I'm trying to get to the bottom of this page, shows that everything's A-OK, hunky-dory. Well, you didn't put cracks in your computer modeling. You showed computer modeling of a structure that theoretically looks great. You didn't show the real world to the computer model. The real world, the computer model dropped the ball because there's multiple cracks all over the damn structure. Where are you? And this is where the forces are coming down 950 kips. It's in fact coming down 12. As I talk about that and strut and tie method here to talk about it. But it's interesting. Strut and tie is interesting. I keep learning about strut and tie. It seems like I'm never done with learning about strut and tie. And now they got a new ACI rules on strut and tie. Oh, it's a lot of work on strut and tie. Um, okay, so computer modeling. Where are you? We're going to find that computer modeling. Forget all that. That's all this stuff doesn't matter. All this math doesn't matter because it's wrong. It doesn't work. It's talking about it in a real, in a undamaged structure. All of it. It's just ridiculous. That's why I state that all that math doesn't make any sense at all. It's not addressing the cracks in the math. It's not talking about the values of what's left of number 11. It states that he has no idea how it just cracked. It just cracked. That's his words. That reported by FIU and roughly by FDOT also. So we run into the computer modeling. It shows no cracks. Computer modeling shows. This is using the computer modeling, dimensional finite element evaluation. So several different loads and load combinations were considered to understand both total state of stress and effects of some individual load components. Total self-weight, so they added that. Stress changes from transferring the weight of the span onto the shims, so they did that. Stress changes from stress or slackening the post-tension bars in member 11. Well, member 11, well, they don't, they're in number 11, but they're in the canopy and they're also in the deck and they're also in the cantilever. So I find this to be limited, and it's direct talking about in number 11. Number 11 sounds like it's just a compression in 11 that was created with this, but it acted as clamp force also for 12. We know it acted as clamp force. That's how they transported the damn bridge, using that as clamp force. This is still part of the computer modeling, and this is talking about that. When the span was placed on the shims, are the stresses on the shim diaphragm essentially equal on the north and south faces, or is it more highly stressed? Well, this appears to be the north end. Whatever the opposite. No, this is the failed end, and it shows it like this. The results indicate that the stress changes in the north and south faces is relatively uniform when the load is transferred to the shim. I had relatively uniform. Look at the wording is used. It is uniform because the shims were placed uniformly underneath of the structure, meaning spaced equally. So you can say relatively uniform. That's not cheating, if you will. It's nefarious because, yeah, there's only 2 points of load points on the one end, and there's 4 points of load points, 4 shims on the other end. But you could use this wording to be nefarious. Relatively uniform, relative to how they're placed, they're uniform. So this is a true statement, but nefarious as hell, I think. Total stress went on shims. Now here are the 1, 2. These are the shims on this end. And this is showing that it's not quite equally loaded. Out here, you can see that it's at least loaded over here on the outer edge from the center line being here. That's that cantilever I talk about. Interesting, so that cantilever is, with all 950 kips coming down it, it has this shape, which actually less load than what you think it would. It is actually putting more load to the right of D1, down D1, D2, than it is going down what reportedly in this same report where it's 950 kips going down. It has it moving the loads out to here. So the question I ask is, are they using the anchors in this too, in this diagram? Apparently they're not using the anchors nor grouting. It's talking about shims at this point. Diagonal crack pattern. Now we talk about, let's do both the hand calculations and the 3D volume element analysis concur that some cracks of the nature photographed are possible. I don't see where this 3D element says that. It shows the underside, and I don't see any cracking here, but they're saying it's loaded here like this, showing red. So it's saying that would be a crack area. Well, if that's the case, you should have addressed it. So I find this to be just BS. This is just a BS statement here. Why the cracks did not develop in the casting area is likely related to the having a substantial portion of load carried into. Why the cracks did not develop in the casting area is likely related to the having a substantial portion of the load carried in the central area. Center area. So diagonal crack pattern. Are we talking about this diagonal crack pattern here? Where exactly is diagonal area? And where is this support area? Now, I could go two places with this. Let's talk about the central area. Are they talking about the mid-support span of the entire structure? The 175-foot mid-span? So you're identifying that you were under, that this thing is deflecting in the middle? Okay, let's say no to that one. You know, I'm not saying no. I'm just saying let's just say no to that one. Let's talk about the only other option is that I can think of is they're talking about here. Is that it was fully supported here, and that now they're saying that it's not supported here. Aha, let's go with that. Because that's what I state that Denny Page states here too, which I stated a long time ago. But he states that it's because it was not shimmed under here, and the shimming would have stopped it from dropping down when they detension number 11. That's basically what I extrapolate he's stating. That it wouldn't have dropped down, and so therefore we wouldn't have had any deflection between the canopy. It wouldn't have kicked out. It wouldn't have kicked down or out. That's very, you know, it's very interesting. Would it have slid out? Would it now had the slip shear that they talk about? Yeah, a couple people want to do it. Would it be at the bottom of? Would it be at the bottom of here? Well, if it did move outwards and break from the deck and you detension, then you would definitely say that, well, forces are going down 11 at that point. But 11 couldn't elongate, so you would still get the same failure if you saw it slip away. If you had cracks, it would still be the result of the same thing that the midspan could. It would be a different failure altogether. In fact, I changed my statement on that. All right, having the smaller cracks on the permanently exposed face, having the smaller crack width. Well, I have no idea what the smaller cracks are. They all look significant to me. But having the smaller crack width on the permanently exposed face, so permanently exposed, is preferable when compared to the other to be embedded diaphragm face. So yeah, he's saying, this is an I wish statement here. One's better than the other. So okay, that's an I wish statement. Oh, I wish it was this way. This is just added I wish. So you know I love psychology. So he just added I wish in here. I mean, why would you expose your mind in that capacity? He just exposed in his mind that he wished that this happened over that. Okay, you just told me what you wished. It is unclear how changes in direction, it's unclear how a change in distribution of the contact pressure on the bottom surface for being supported like this for several weeks. So for several weeks, they added this new support here. This would act as what? Again, these bars here, right? They stopped it from hurricane regions, you know, the whole 4,000 pounds they had on the ground. You know, I don't know if it's 4,000 pounds. Those look like similar to Jersey barriers, you know, a yard of concrete. You know, what do you call it? 2 yards of concrete on one side and 2 yards on the other. You know, we're talking 10,000 pounds, you know, and these anchors go back to one thing. What were the intent of those 2 blocks? Were they designed to keep this from rotating left or right? This thing had a damn torque on it. So that's what I'm talking about, torque here. Is this bridge had, sitting on the pylons here, this full base. Why these? Well, the whole 10,000 pounds, all right? So 10,000 pounds isn't a counterforce for this. If it could rotate that over and twist it, 10,000 pounds we know is not the counterforce. You can call it 50,000 pounds if you want. It's not the counterforce for this bridge from rotation, right? What if it was lift? Say the wind was coming this way, the rotation would then push down on this, so that would create the base of that would then become something. It would have to an anchor point where it would have to push into the ground or slide across the ground, right? And so it's on whatever soil is there. It would friction would let it slide across, and then we also have to talk about the supports. These pipes. What point are they all equally loaded? Are they 100% all equally loaded? Is one a little more tight than the other? They use like a turnbuckle. And at what point do they fail under? What do they buckle under as this would rotate? What the hell are the intentions of these is what I'm asking. What are the intention of these two things here? I don't understand the intent of these guys at this point. I don't understand the intent of it. So I'm pretty much washing them. I don't see them having an effect during my whole conversation. So I don't see them having an effect, so I wash them out. I wash them out, as far as, the wind lifting this thing up. It is a million pounds, but it is a damn umbrella, I call it. The underside of this thing could have some uplift. Who knows? Yeah, they know. This is that cantilever I talk about. But to being supported on the bottom of 4 shims. So 1, 2, 3, 4. So now they're saying that now he theorized that, well, this would create a higher load point here. Let's go here again. So he's saying his computer program says that. So bear with me, guys. I know where I'm going with it, and so this should give you some interesting thought. So their computer program states that stress changes from placing onto 4 shims. So he's first stating that it's fully, in the report, it states it's fully loaded in OSHA report, FDOT, and FIU. That they all state that this is fully supported underneath of here. That means full contact, not shimmed. So it's full contact sitting on this bent on this false works. So it's not shim loaded. So he's now stating that running the computer program now and now putting it under shim load, it looks like this. With that said, he now states that it is unclear how a change in distribution of contact pressure on the bottom surface, contact pressure, point loading they call it too, right? So for being supported like this for several weeks, it's called point loading also, or contact pressure, right? Is what he's talking about. For being supported like this for several weeks. So he's stating that, well, look, we had no problems when it was supported fully like this. Why all of a sudden do we have a problem now once we detension? Well, me, I state that, well, because you lost your clamp force in the bottom, and he's stating that it's no longer fully supported under, and the image is very terrible. I would love to see if it's fully supported under here, under this cantilever, I call it. And now he's stating that the computer program states that it's supported now like this, and then we're going to go, I think it goes back to the computer program again, could possibly cause this top. Now, he said he has no idea how it's called, but now he calls it spalling. He identifies this as spalling. This is not spalling. Right? This is not spalling. He calls it spalls, rather. Then he used the computer program to show this, and we're using the 4 shims, I believe, still. The total plotted as principal tension stresses from the 3D models are. This plot has the diagonal post-tension bars in member 11 de-stressed. So once you de-stress, we don't have, the computer model doesn't show a sliding, so the computer model, so let me have a little, and I shouldn't, but let me attack the engine tips group. They have, and I say attack, they keep asking me, I look over there now and then not much, but I look over there, and they keep asking me, the one clown, Earth guy, keeps asking me to prove my stuff. Well, you guys all call yourself structural engineers. And you hide behind weird names like Earth and Cubicle, whatever the hell you call yourselves. All these weird names, right? None of them are human names. So you do a damn video. Do a video and show me errors of my ways. Show me your intellect. I am always willing to change my position. Always willing to change my position unless I have a conclusive file. And I don't have one on this. I'm always willing to change my position as data comes on. This could be a computer model that he's holding back. There could be multiple other evidence computer models that show that, oh, look, there's slip shear taking place here. And maybe Denny Pate didn't show it. So I'm always willing to change it. But this model is what they're showing. This is the model we're working from. But I'm willing to take on that data. This model shows the cracking. It doesn't show up here any further, but it shows this base having that crack. And it looks like this might be our torque failure, our torque crack if we look at the issues of it. We see that it's stressed in D1 area. We have some high stress, that spalling as he calls it, then a holiday, and then some significant loading here. Now, it said the 3D model. Let's trash the 3D model ability, its element model ability. It should show jack shit right here. There's an 8-inch hole here, 12-inch hole here. It should show no stresses in there. It's a hole in the damn deck going through here in the diaphragm. So how can it be so it's loaded across a hole? They should show it around the hole. So I find that weird. That's sort of, it's like showing this solid over here. They show this is voided, and the underside apparently voided. They show it voided between 11 and 12. Well, they should show a void here. So apparently this 3D modeling shows this is a solid diaphragm and does not show the voids created by also the post-tensioning. This just shows a solid decking. The post-tensioning and its trumpets have voids in the diaphragm. How come this isn't showing a lot? This 3D element isn't showing a lot of variations between all those post-tensioning. And how come the 3D element isn't showing it? Is showing it so equally balanced down this diaphragm, down the deck. This appears to be the loads from the transverse post-tensioning, while the 3D elements is showing that it's stressed highly over here on the highly compared to here. And it doesn't show it really taper off. It just shows it really compressive on the ends. So it's a weird 3D element model that they're showing us here. And this I find very intriguing. This side action here and right here. This path. This right here. And remember, they had anchors in there, so holding it in. So why isn't it also different now, voided? Those anchors they're showing. So I find this to be, lacking in this model that, I don't know this 3D model element, so I can't really critique it much. I just find this, using logic, that this model, I would have to bring this up. Why aren't we seeing the post-tensioning? Why is it showing fully solid here, and yet there's a pipe there? If this is fully solid and this is taking on the same load, we should see a pipe that's cracked. We should see a failed pipe. Basically, I should put my hand in that pipe and it would just crush, disintegrate. It would just be, terrible. I'm having a little being facetious with that. I do understand that the loads are in this capacity. Let's talk about why it's voided here. If the loads are supposed to be here, and Denny Pate argues that it's supposed to be shimmed under there, the 3D model says otherwise. It says the loads are going out left and out right, which would, to me, would be the loads are coming down here, 950 kips, and it's creating a diagonal shear, which I'm kind of biased on. Remember, I already talked about that. The loads coming down here, diagonal shear, and that kind of does skip there, doesn't it, in my theory? And wait a minute, this 3D model has it as voided. So Denny Pate arguing that it should be shimmed under here is so critical. The 3D model says otherwise. I'm sorry, this 3D model that we're looking at, it says otherwise. On the back end of this, and I like to say a end, on the back end of this, it shows it as, hey, it's a freebie down here, that there is no loads pretty much in the center line, thereabout center line of this cantilever. that it's on the outside edges of it, but the center is kind of free. This is encompassing that diagonal. So I am talking about, I don't care what the, I do care because it's going to be awesome to look at, but I don't care what NTSB determines. I don't think they have the logic to determine what's taking place. I think they have that NTSB, if you think about it, guys, NTSB just goes through airplane crashes, and they used the data, the flight data recorder, to tell what was happening before the crash. And you just see what's the deviation. It's kind of simple as that. What deviated? Well, he used his flaps. Well, he was going 100 miles an hour and he used his flaps. Well, what effect would that have on the plane at that altitude and that speed? Well, that would make the tail end drop, and the plane just now is uncontrollable, and they try to recover. What do you do next? It just records everything they did. We don't have a record of everything they did. We don't have a true record of everything they did. NTSB doesn't have the ability to do this. If you look at their investigators, and I've looked at their investigators, one was a cop at one time. Their engineer was a cop at one time. How ironic is that, right? So, does he have the ability to do this? Apparently not. He's not stepping forward. They're blocking data. I wouldn't be scared to block data if I'm talking about it. In fact, I'd put it out there, and then I would surf the internet too to see who could help me out with some direction, because that's the way I am. I'm not so bosun and brazen to say I don't need your help. In this case, I am with NTSB at this point. With all that said, if they mirror my report, I have to say NTSB is an outstandingly organization, and they're very intelligent. Sorry, guys, I had to say that, right? So I'm smiling here. So anyway, so there we go. This is still the computer model. So this computer model says otherwise. If we wait for the NTSB report, we're waiting for. They've been lobbied. Who's lobbied me, guys? Nobody's lobbied me. I'm just using the data. I'm using sound logic is what I'm doing. They're using engineering to tell you that this slid off. They lost logic at that point. You can use engineering, but you have to have logic in your engineering. The 3D modeling, and I'm going back to attack the idiots over the idiots. Those are the idiots that have no logic. And so if you don't have logic, well, you're an idiot. Sorry. That's my, well, and that's wrong for me. I have a new position in life. So I apologize for people that don't think logically. That's wrong for me to say that, because some people don't think logically. They see things differently, and I know that now. So I apologize for that statement. So they don't have the ability then to think logically, to see that the 3D model, if you go by this, hundreds of thousands of dollars of programming, it doesn't show sliding here. So if you state that FDOT states that you must use 3D modeling, and it's been now done by FDOT, it's been done by, we could theorize, FIU somehow, and it's been done by Berger, we believe, and OSHA, I think, did it twice, or they talk about it 4 times. It's been done all together. Anyway, none of them appear to show this super red. They don't show this super red identifying a red failure there. If that's the case and it really punched through, then all these 3D modeling programs and Denny Pate and everybody else should be let free 100%, because they were told these are the rules we play by. And if you play by these rules, then you're okay. And they use 3D modeling. 3D modeling says no sliding, punching, shear took place. Denny Pate, for him, could argue that, hey, look, I used 3D modeling, and using OSHA report, Denny Pate argued the OSHA report was false. I would have argued, if I was Denny Pate, the OSHA report proves that I'm innocent. The OSHA report states that punching shear took place. In that case, I use 3D modeling, and 3D modeling does not show a punching shear. And so my 3D modeling software led me astray. And per FDOT's guidelines, I used an approved 3D modeling software that did not show this failure. So therefore, I am innocent. And FDOT needs to correct its guidelines on telling me how to be an engineer. how to engineer something. So in other words, if I use 2x4s on all two-story buildings, residential, right? That's the code. I'm good to go. I'm safe as long as I don't overload them with some weird ass, siding, just a typical siding. I'm safe all day long, all the time. In the same development area where it's allowed, all the time. If some magical reading, all the studs fail, well, nobody goes to jail. It was the code that said you can use 2x4s on that. So that's my argument for Denny Pate, that he should have said, oh my gosh, the OSHA report exonerates me because it said punch and shear took place. Oh my gosh, OSHA is awesome. My 3D modeling software is no longer awesome. It's the fault. It's the error of the waves. It caused the failure. It's resulting in the failure because I never saw it via my 3D modeling software. You see the way that works? It's a conversely to everything we do in life. And he missed the conversely on that that he could have said, the OSHA report exonerates me and my 3D software should be sued. All right, moving on. Here's the 3D software again. The change principle stresses solely from distressing the post-tension bars in member 11R. And this appears to be 11, that appears to be 12. The analysis neither total stresses nor post-tension bars only stresses. Okay. I can't understand this yet. Neither total stresses nor post-tension bar only stresses. So there's no post-tension bar stresses, neither total stresses. So total, the word total again just kills me. So what do you mean neither total? You got the word total. It's so ambiguous because it's everything again. So you don't have to do this. You just use total, and this is confusing. So, but that's parentheses. But let's move on. Shows any spike in tensile stresses at the corner of the deck diaphragm, member 12. So I can't read. This diaphragm appears to be this way. This is the end. This is the overhang. This is the base. This is zones, I believe, which looking at. These might be the arrows indicating such. This is the color band they're using, which we don't see the scale of it, but using that, red being the most tension, or is it compressive? I don't know what scale they're using here, so that's a weird thing, and I can't just guess it. I can say what's opposite though. I can't do it. You can change your scale, so you can guess all you want, but I am not. This is how I protect myself. Sometimes I don't assume that this is compression. I could probably assume it above, but not in this one. It's a separate drawing. It's the analysis shows any just leave this part up. The analysis shows any spike in tensile stresses at the corner of the deck. Done. So this is really looking at tensile stresses at the corner of the deck. If we leave that out, that's the way I read it now, and I can't even see it. I see nothing. I see nothing also, if that's what it meant. Moving on. That's just their 3D modeling they're sharing with us, and I'm using that. Okay. And so, I don't know if we should use this, but the diagonal type cracks and excessive FDOT criteria should be sealed with approved methods and materials. I already talked about that. He has no idea where it came from. This should not be how you address it. The spalled areas have not been replicated by the engineering analysis. You understand this? That everything we looked at in his drawings do not replicate those spalling. So all his presentation says that he's not replicating it. So this was nefarious in its presentation. Let me show you where I talked about it earlier, where I state that this sort of likes that, doesn't it? But he makes it clear in his summation that this is just smoke and mirrors, that this is just BS presentation, because even though you're looking at that, I am wanting you to think that. This is like a prosecutor, if you will, wanting you to believe that, but disclosing down here that the spalled area has not been replicated by the engineering analysis. Period. It's period. And then he does, however, leaving you to come up with your own answers. And then next bullet. So this is by itself. Next bullet. The spalled areas are minor, and is recommended that they be prepared using normal procedures and poured back along with the upcoming polyline diaphragm. Pour. Different from any prior to the backspan on false work pours. Okay. So he doesn't know where they come from, and he's just saying ignore them and just, patch them. That's all it amounts to. I have no idea how they come from. We can't duplicate them. We can't duplicate them. I can friggin' duplicate them. Let's see. Move the structure over there. Detention 12. Take a photograph of the structure. There you go. There's your cracks again. Okay. Then present this presentation. And then, okay, how do you duplicate them again? Oh, okay, let's do it again. Move the structure over there. Do nothing. No problems. Detention number 11 and number 11. Oh, there they show up again. Okay. I'm being facetious again. They show up again. Wow, I can't figure out how to do it. He says right here, the spalled area has not been replicated by the engineering analysis. Yeah, it's not been but it's been duplicated. You can duplicate it in real life by building the bridge, putting it over there, detensioning number 11, doing the same thing again. That's duplication of it. All right, so I'm just showing you that detensioning B right here caused this to drop down, in which Denny Page argues that shims would have saved it. The engineering software says that there are no loads under here, that it does show forces coming out here and here, so that's your shear crack. They did the engineering software based on this being shed on 4 shims, set on 4 shims, but he did not show it detensioned in his statement. Oops. In their statement, they do not say that they detensioned number 11 during this computer modeling of number 11. So let's go. Let me close out with that, where he states that they used a computer modeling for clarity. I think that's right. Right? Might be going around the circle and have to do an apology, but. Both the hand calculation, the 3D volume elements analysis concur that some cracks of the nature photograph are possible. Some cracks. While the cracks did not develop in the casting area, it is likely related to having a substantial portion of the load carried in the central area. So he's stating it's carried in the central area, but it's not carried in the central area. The central area is showing that the base of number 12 is a freebie per his 3D element. But the outside of the base is not. So it's center line outwards is where the load is going. On diagonal, 45, there's shear. It's loading. Having the smaller cracks with the permanent exposed face is, that's that wish thing, hold on. How the change of contact pressure on the bottom surface. Right, he talks about that. And I'm just making clear that number 11 was not shown as detention. Right. So this is what he shows. So going back to this one. It is unclear how a change in distribution of contact pressure on the bottom surface from being supported like this for several weeks. So supported like this, that means that number 11 is post-tensioned. It has B connecting it, and also it's supported there. But number 11 has a clamp force. So remember when they built this, they did D1s and then C2s, and then they post-tensioned number 11 without grouting it. So they put a clamp force down there, and then they continued the rest of the deck. And then they released that clamp force, and voila. So they're being supported on 4 shims. Could possibly create these top spalls. So you see what he did? He jumped from being supported on these 4 shims, he stated, and in his presentation, he just jumps to created this. This left out the one stage between creating this, detensioning number 11. And this is an engineer, with structural engineers underneath his belt. I don't know if Denny Pate, is he structural? It doesn't matter if he's structural engineer or not. So he's left out in his own analysis that detensioning 11 took place between this to this. He made the jump, and this is what a prosecutor would do. They would do this, and then in your brain, you would go, oh, wow, that's weird. But you're leaving out, and you're allowed to leave it out, right? He left it. Oh yeah, I left that out because that's what he wants you to do, to make you believe that it went from there to there magically. You detensioned. So the only thing detention did was take away a clamp force. And now you got to tell me what effect that clamp force had. That effect of that clamp force had the effect of causing these cracks right here. We're looking at it. We're looking at the effects of detensioning. That torque, that rotation in the canopy, that caused the rotation just like a long pipe on a nut. That caused, because it happened immediately as the guy's detensioning stated, it cracked like hell, had the effect of rotating the base of 10, creating that imbalance of torque, that imbalance of loading on the transverse post tension cables, that torque effect, which loaded this incorrectly and caused a brittle failure of the deck and the canopy. That's my NTSB short version. This is the short version I have of how the failure should be explained by the NTSB. The long version has all the other friggin' details in it, which I don't think I'm gonna make. I don't think I'm gonna make it. But that's that rotational torque right there. Now that really helps me explain why the loads went down 10, even more so. I really like that. Hope you guys like it, and I'll see if you got any comments for me, and then I'm going to do a Houdini on you. I'm going to disappear. Where are you? Live video over here. Oh, wow, they show the comments here. That's cool. This is what I'm stuck with now. And you can see YouTube is not receiving enough video to maintain smooth streaming. I have to put up with this a lot, with this new learning curve of the YouTube's beta program. Where are you? Let me see your comments. Yep, had to try the old system. Okay, here we go. YouTube is a joke. How do I stream like I did yesterday? I scheduled an event and now I can't where to go live. Yeah. Wait a minute. Well, I had to go there. Yeah, everybody has the same problem. I had to go there too. And it turns out you just got to press the one button up here, go live. It took me forever last time to do it, and I duplicated the same problem. All right, let me just go to Luna and go under Luna. Brooklyn, hi everyone. Hey, Brooklyn. So you guys know, I think Brooklyn is pretty cool, especially in light of my previous video talking about 1 out of 4, 3 out of 4. If Brooklyn, I'm talking in code to Brooklyn now. That Brooklyn is pretty cool with evaluation on that. Duct tape, unbelievable. Cheap labor. Well, they're hiding something with the duct tape. I have no idea what Brooklyn, but it wasn't shown before. And why duct tape it? It really risks people's lives. Hi everyone. That's Wombat. Hi Wombat, right? Yeah. Welcome. Is there a new doc that's been released? Only that they're going to do a 22nd October live presentation, and it's craziness, right? Because they brag about, I showed in the video, they brag about sharing all the data with the train wreck. Thousands of pages, they say, thousands of documents and photographs. Not meaning and thousands of photographs, but thousands of documents and thousands of pages and photographs. But yet in this one, they went to court to stop presentation. And if you look at my other videos, I talk about how the NTSB is being lobbied by FIG and their other named company, apparently other named representative company of that I showed, whatever they call themselves, lobbying NTSB, and it appears to some effect, because we had a state court in Florida state released the documents, and then all of a sudden NTSB comes forward and says, stop it. Don't release the documents. We don't have OSHA coming forward saying, stop, don't release the documents. So and OSHA gets a pat on the back. But NTSB comes forward and says, don't release the documents. We want this hidden from the public. and yet you're going to doing what they said, the sunshine law or whatever, that they have to release it to the public. So I'm doing my FOIA request for that, but isn't that just a friggin' waste of my energy? It's just a waste of my energy, because we know that through, well, if you want to predict the future, you just look at the history, the data. The data says NTSB is running a block against the public. I mean, they literally have a court order and federal injunction saying stop it. Isn't it federal? They went to federal court? Did they go to federal court? Oh, they're federally. I'm sorry. They're federally. And then they went to a higher court. Right. So the federal government went to a higher court to say don't release to the public data we have. Like the public can do something about it. Like the public can control. So this is the way lobbying works. So like the public can control the outcome of this. Well, the public really can't control the outcome of this. Who controls it is lobbying. Lobbying controls it. And here's why there's a Democrat and a Republican Party. Because and the truth of it is not because one represents left and one represents right. Because it's frankly, if you represent the other side, you get paid for representing the other side. But if you both represent the same side, if there's 10 of us and 10 of us and we're all on the same side, all I need to buy is 6. And maybe 3 of you already are on my position. All I got to buy is 4 more people. I got 6. I don't even care what the other 4 people think. I only have to buy 4 people off. So it works this way. If I'm the NTSB and I accept lobbying and I like money, because they like money. NTSB does like money because they accept lobbying. They didn't ask to be exempt from lobbying and say we should not be allowed to be lobbied. They agreed to be lobbied. So if you agree to be lobbied, that means you want money. By conversely, you want money. So that's like me telling you, I agree to be lobbied on this subject, guys. And that means I accept money to change my position. That's what I'm saying to people. I'm not saying I agree to talk to you for money. I'm saying you can. We know what lobbying does. It sways the direction of vote. So NTSB says, you know what? I'll do my part to show you that I'm willing to lobby. I'll protect all parties, all parties that are party to this possible criminal complaint. I'll protect you. I'll go to court and stop all public documents so nobody will be attacked. But I am the one that's going to be able to release those documents. I will control them because I'll get a court order that states that nobody will be able to release documents until I decide that I want to go to the court and say release these documents. Because I find this kind of strange. If there's a court order existing, well then NTSB should not be allowed to do a sunshine release, stating they're going to come do a public release, because there's a court order existing saying that they can't release information. So how is it possible that they can release information? And that's the basis of my FOIA request, is saying, look, they've got schedule a 22nd. You schedule a 22nd public hearing on this thing, releasing all the data supposedly. In that case, the court order must have expired secretly and nobody knows about it, because they're going to violate a court order. I mean, come on, bite me, right? I feel like cursing, right, when I'm saying bite me. So and my man over there, Earth, says I'm conspiracy nut. Bite me, Earth. You're from. I actually have family family from where he's from. It's in Australia, so I can't really attack Australia. I'd like this talking, but I got family there. So anyway, and I'll teach you that about bias and racism. You won't be racist against or biased against people that you might have family related to. It's kind of an interesting thing. So if you got some bias or racism against a nationality, you probably don't have any family related to that nationality. Ha-ha. Think about that, guys. Because it would be attacking you to have a bias against them through third party, unless you don't like that person's connection to that nationality. It's just, psychology, brains. I just love it. See, I don't have a problem with racism, and I know it exists. But it's a bias. It's not really racism. It's because the way the Creator created us. Moving on. So NTSB states that it shows, I'm showing you guys, pretend like I'm the NTSB. Hey, look, I'm holding all the documents. And I can take lobbying. So I can't talk to you directly. I tell you straight up when you try to talk to me, no, we can't talk about that. I can't talk to you, and I say it this way, I can't talk to you directly about that. I just use the word directly. You know now, if you got any brains, that means you got to lobby me. You can talk to me through a third person, a lobbyer, a lobbyist, but not you directly. So you make a donation of $125 plus $1,000 so far. I think Fig did, right? I'll listen to that person. That person says, "Look, man, we got think about the infrastructure. This is the lobbyist talking now. I'm talking for the lobbyists, and I'm trying to convince NTSB. Now, I'm being serious now, guys. Sound like I'm a lobbyist, and I'm not. So don't try to sue me, any federal government, for saying I'm acting as a lobbyist. It's a pretend. This is whatever it is pretend. So don't friggin' lock me down. Anybody trying to say I'm acting like a lobbyist. I'm not a lobbyist. So if I was a lobbyist, I'd say it like this. Look, NTSB, this is why you need to find that this was just, let it be swept under the rug. Because, look, we're Fig Engineering. And Fig Engineering, we got bridges all around the country. If you were to find against us, this would then make the whole infrastructure unstable, because now it's going to cost all these states. The states, now I'm talking money to NTSB because they have an interest in states, right? Money and all that. It's going to cost all these states hundreds of thousands of dollars and possibly millions of dollars to go back and investigate all our work, because you're going to find that we were inept, that we lacked this engineering ability to do this. Not only that, we also, other people depend on us. We have, thousands of people that depend on us, such as MCM, that will trust our engineering, that use it. This was one mistake. This was unforeseeable. This was a new design. We think that it was actually MCM's fault because they didn't follow our shimming rules. All right, end of lobbying on that, they say. It says, end of your session. Have a nice day. I'm like, son of a bitch. So remember, I'm the lobbyist, but now I'm also acting in TBS. They're like, that was nice hearing you. I'll consider that. And then I ignore you. You're like, son of a bitch. We got to go back to him again. So you show up again with me for another $68,000. I start the clock again. All right, go ahead. Continue your conversation with me. Well, look, we own a couple of bridges too. We manage them. If you get rid of that bridge, we're going to have to shut down that bridge. That's going to stop the crossing of the road from there to there. The insurance companies are now going to be involved. You attacking us is going to cost millions and millions of dollars now. And then you went from 100,000 to now I'm regrouping. I need to show you that the federal government's got sweat in the game in this too. That if you destroy me, Fig Engineering, I'm acting as all parties now, I guess, and everybody, then you also will cause a drama around the infrastructure and around the world, because I have bridges around the world too. So you destroy me over one bridge and you destroy infrastructure around the world. This is why you need to find a way that shows that clearly, that it's you. We can't find the way either. Nobody can find the way. Nobody saw that. So you need to find the same thing. That you need to find multiple conclusions. Beep. Time's up. You're like, son of a bitch. So then he's got to lobby again. They come back because you see Fig is giving them multiple thousands, right? Each one's not free. It's not just sent in the mail and no conversations taking place. Clock back on the clock again. All right, we're back on the clock again. Look, you need to find NTSB. You need to find multiple conclusions that state that what needs to be done better next time. But you need to find that you need to be ambiguous on your fault, because if you find fault with us in any way, we're going to spend our last dollar to lobby that the NTSB is inept. Now attack the NTSB. And NTSB, you son of a bitch, you actually telling me that? Yeah, because if you try to ruin me, I'm going to lobby everything. I'm going to lobby against NTSB. That's just one of our positions. I'm just telling you now that we're going to play hardball too. That's the way I do it. And you're like, you something, time's up. I'm like, oh, okay. Well, I'll come back again perhaps. Or maybe I'll let it ride at that and I'll walk away. Now the head of some wall sits there and he goes, son of a bitch, he's going to lobby against the NTSB? Wait a minute. Or is he just going to spend his money and lobby against replacing me as the head of the NTSB and then get a new report put out, or a supplement report or something, or just replace someone? Is he going to muddy the waters? You're like, all right, well, you know what? That's the way lobbying works. That's the threatening way. The threatening way, remember, threatening way always puts somebody on attack mode back. So that's not very good. So you have to give somebody an out, and you always keep lobbying. And now let's go back. Let's go back to lobbying this direction. So look, as long as as long as you can find this in this favor, we are totally always going to support the NTSB. I mean, we'd like to see you next year after the report comes out and talk to you about some things we think are structurally important in the world. So you see how I invested? I already gave them more money in the future because it's about money for them. I gave them more money in the future once we have this discussion. Once you find after the report shows that it's so ambiguous that we can't really nail it down, that this is the magical bird that landed on the damn structure. Oh my gosh, guys, you won't believe about the magical bird. You know I make joke about the magical bird. Well, an engineer sent me a video of a collapse in 2014. Was it in that Indian country? I think it is an Indian-based country, Asian, India. Anyway, it's a mosque, Scone, C-E, the link, S-C-O-O-A-N. I'm sorry, remember the acronym. It's a mosque or something. Well, they're claiming this plane that kept flying over, and they show the video, what's going on with this plane. I'm like, you're shitting me. The magical bird I joked about, that I said they want to find a magical bird that landed on the bridge, it caused the collapse. Well, they actually using that as a defense in that, you got to find the video, in that damn structure collapse of the building. They keep showing the helicopter or plane going around the structure. They say, look, it's coming over 11:15, 9:15, all these times. Like, you're shitting me. It's a plane, a bird, get it? I'm smiling now because people joked about my magical bird, and there it is. Somebody's using it as a real defense. So I have to be careful, don't I? And they used it way before. Well, no, I don't know when they start talking about the magical bird. I didn't look at the timeline on that, but the video shows that, and then they start talking about it. So anyway, I'm smiling. So you need to find a magical bird, something else. Okay, you take it on. I can give you a ride. Yeah, I'll give you a ride. Just give me a couple minutes. Downtown, right? The other direction? Okay, good. Yeah. All right, then I'll wrap this up. So look, so that's the way the lobbying thing works. I just wanted to add that in there. So what do you expect to see from the NTSB? A real genuine attack, which I've seen Sumwall attack once people don't follow his recommendations. So apparently he made recommendations previously, and when the train track, I'm using the train one, had the same failure, the switching, he then made this video of a very aggressive nature saying we don't support it, and it was it was nice to see that aggressive part. So I don't throw out the baby with the bathwater. So I don't find Sumwall's not releasing public data on this fair at all. And fair, who gives a shit about fair in real life, right? But on that part, now talking good about Sumwall, is that, wow, when he's angered, when he's feeling attacked, his conclusive file was attacked. He attacked back in that meeting. So it shows that Sumwall can attack back, but only if he is attacked. If he feels like his conclusive file of what should have been done was attacked, then Sumwall will attack back. Otherwise, Sumwall under the payroll, baby. That's the end of this video, and you guys don't have to really pay attention to the end. I appreciate the little thumbs up here. And what else we got here? Let me refresh this page. Refreshing the page, for me, on my side, you guys will see it. It will say if anybody, I guess, I don't know if this new thing works. It would have showed comments here that I have to address and that I read first. But it doesn't show it at this point. Doesn't mean it does. It's not there. Okay, so that's where I ended. If you got any questions, fire up. But it's more about torque action in the Canopy. Release of via B. Oh, and that's showing that this Canopy was not symmetrically loaded. If this was symmetrically, so it was not symmetrical. That the forces in this design down here, for sure, were not symmetrical. And so loss of symmetry down here causes rotational torque. Symmetrical, maybe it would have just dropped straight down. The forces would have been equal. But then again, it is pivoting on a bar. But the Canopy, you think, would have been symmetrical and keeping it so it would fall down equal and parallel, because this is supposed to be parallel. So when it had that original moment, that bump, that you think this Canopy would have made this made this drop or move any direction equally, but we see the tape measure reveals that it didn't drop equally, which shows a rotational torque again, and that reflected itself in the canopy, which reflected it down 10, which also reflected in that in the very apparent photographs of the torque in number 11. I'm going to end it with that in the torque of number 11. So that's my NTSB version of a good report. Not claiming to be NTSB and not claiming to be any federal official like that. So don't try to jam me up and lock my ass up on some shit like that, because your feelings are hurt. All right, so there's your rotation. Don't try to use my words in that. I claim to be Joe Nobody. That's all I claim to be. So anybody wants to put that on, I'm Joe Nobody. There we go. Don't try to put me in any damn category where I'm trying to claim anybody. Okay. Take care from Joe Nobody. That's the rotational torque. Love all you guys for watching this stuff, man. That's in a real nice sense of saying I really appreciate your time and that you guys are really interested in this topic. Where will it go? Nowhere. We don't have the lobbying money. They paid hundreds of thousands. We paid zip. Now, I think I end this by going here. No. I have to go over here and end stream here, and then this ends that. All right, take care, and yeah, they make you do multiple steps. So, like view, current views, this is interesting. I don't know how fast it is. It says, here's a stream, DVR, so you can play it back. What's all this stuff? Let you look at it too. Change the latency to very different to help you be able to respond faster. I can change the thumbnail there, whatever that is. I won't show this because it can be the any lobbyist looking at this would then be able to use the data behind it and go, ha, the interest is not that much. Don't have to worry about them at all. And they don't worry about it really, but they still take on research. Lobbyists are pretty damn smart. They research everywhere. So I don't underplay the power of a lobbyist or the knowledge of a lobbyist. They know they copy, they follow the internet, and then they know what to counter and discuss about, assuming that their opponent is following the internet data. And we know that if we look at the